Hello again, and welcome back to my series about object detection. Today we will talk about SWIN transformer again, this time focusing on reading the source code. So first, prerequisites. I do assume that you understand some basic principles of SWIN transformer. If you don't, I have a great video about that in my channel. Also, you need to have torchvision repository set up. I have a different video about VIT transformer that goes through the setup in length on how to install all the dependencies, how to debug the code, and so on. So in here, we just follow the same footsteps. So if you don't know how to do that, just look up the first 20 minutes of the video. I will link it in the description. And here's the plan for today. So we'll start with just overview of what different model versions they are, what data they use, and so on. Then we'll go through the Pytorch torchvision implementation, starting with just data loading, what sort of data even comes into the model for training, what data augmentation techniques are used. Then we will just read the forward call of the model, look at the overall structure, the attention blocks, the patch merging operation, and so on. Then we will discuss an interesting technique that is not really from SWIN transformer. It's quite old, but this is the first time I've seen it, called Stochastic Depth. Then we'll look at the core of the model called shifted windows attention. And finally, we'll look at the code for the patch merging block. And so let's start with just model lineage overview and versions. So the model itself was trained by Microsoft. They published the paper, and they have their own transformer implementation for that. It's also written in Pytorch. However, this is not the one we will be looking at today. Today, we will look at a different implementation from the Torch Hub. It is located in the Pytorch Vision repository. So if you were subscribed to me for quite some time, you'd know that we have seen this repository quite a few times already. So we've looked at the code for ResNet. We've looked at the code for VIT transformer. All of that is re-implemented in this repository. So it's quite convenient. You can set up it once and then read the code for training and for inference for a lot of models. And this is the one we'll look at today. It uses the same data, which is ImageNet 22K for pre-training and then ImageNet 1K for fine-tuning. This is exactly the model version that is hosted on Torch Hub. So if you download the weights from Torch Hub, they were achieved by training using this recipe from this repository. And so here I'm located in vision/references/classification. So you can take a look around in the repository. There's a lot of stuff there. They have tutorials, training examples for object detection, classification, optical flow, all of that. So it's quite a good source of knowledge in general. Once again, as I mentioned, we will not go through the setup right now. I assume that you know how to do that. And so in one of my previous videos about VIT, we've basically set up this Jupyter notebook located right inside the repository itself. And so if you do that, you can just start the Jupyter notebook, just execute some blocks, and then just copy around some code from train.py into your Jupyter notebook and actually execute it. So it's really convenient because it allows you to play with it more interactively. Like here, I'm just loading some images from the dataset so that I can actually look how they see how they look like. So we've gradually approached the question of data. What is the data? How do we load it? How do we augment it? So let's talk about that. So unlike Vision transformer, SWIN transformer does not use this enormously huge GFT dataset or SWAG dataset from Meta. It's trained on publicly available datasets like ImageNet 22K and ImageNet 1K. So you can understand what it is by just Googling ImageNet. So technically, you need to register and write to them to get the 22K version, the big version. The 1K subset is freely available from Kaggle, so you can just download it from here. And here's how it looks like. So typically, it's just an image of one object, like bananas in this case. Although some of the images also have bounding box annotations, this is not what will be used in SWIN transformer training. So SWIN transformer trains just classification. That's when you get an input image and you need to predict just one class for it. Thanks to this Jupyter notebook, I can actually look at how images look like. And by pressing this execute cell button repeatedly, we might get a sense of augmentations that were used as well. So we can see that the image, the colors change slightly, the image gets cropped. Sometimes there will be this random square or rectangle cropped out from the middle of the image. Sometimes, I think this one is called solarize, where the colors are just weird, and so on. So you can actually look the code for that if you see the parameters. So it is using an augmentation technique called TA wide. And then coming back to code, I can just right click on that and press go to definition. And this is the actual loading data code from torchvision repository. And so here we can see that we basically initialize this torchvision image folder dataset, which works with datasets in ImageNet format. And we provide the classification preset. And that's basically the set of parameters, augmentations, and so on used. And so TA wide uses this trivial augment wide. And we can again just Google what that is. Right, and so this is the alternative implementation of auto augment, where we basically have a bunch of transformations we can do, and then we apply one of them at random. And so coming back to our code, we can see that in action. So yep, just random transformation. Sometimes it shifts the window, rotates the image, crops it out, zooms in, zooms out, flips from left to right, changes colors, and so on. All of that is needed to basically enhance our data, to generate more unique examples where we still are sure about the class that the model will actually need to predict. And also, it's a good way of making sure the model just doesn't remember all the images from the training data set and just keeps seeing something new to make it more generalizable. So this was the dataset code. And the dataset is when we just provide one index and get an image in return. And here is how we can take a look at labels. So like this, yep. And 0, I think, stands for human. Right. And then we also have the data loader code. So data loader is a thing that actually loads the data from the data set, combines that into batches, does that in parallel, does that with buffer so that your GPU actually always works and doesn't wait for disk I/O before starting to process the next batch. And one interesting thing here is that it is mix-up cut mix. So what it does is it basically merges several images together, and we'll see that in a minute. So it takes a batch of images, several images. I think in our case that was 8. And then it takes 2 of them and just merges them together. So you can see one image sort of overimposed on top of another image. And we can plot a different image in a batch. Yep, again, just some image superimposed with another one. And you can execute it a bit more and see how different images combine like that. Yeah, so here one image is extremely rotated, and then another one is just there at the center. And then this one, I believe, contains the second part of the image. And again, now the second part is the bigger picture, and the first one is smaller in the down left corner here. And another interesting detail here is that initially we started with strictly one class per image. So this is the label format that we had. So we had an image and then just one class that says that's a person. Now we merged 2 of them together. And to deal with that in labels, we just create basically logits, so probabilities of every class. And in this case, 2 of them will be non-zero. So this is like saying, in this image, we have merged, I don't know what that is that a pipe and image of a flower or something like that? So we have a pipe, we have a flower. We took 30% of the flower and 70% of the pipe, merged them together in this peculiar way, and then the labels will correspond to that. So the label will say that it's 30% pipe, 70% flower. That's a tricky case. And this is basically it about image loading. So once again, we can look at the shapes for that as well. And we can see that all the images are actually downsampled to the same resolution. So it's quite low resolution, 2:4 by 2:4. So it's not HD, it's not proper resolution, but it's enough for pre-training at least. So that's what has been historically used in ImageNet. Now, final thing, now that we have an image, we have it in our Jupyter notebook, we can actually initialize the model. And this one is called SWIN Tiny. And then just apply the model to our images and get out the output. So the output is again 1,000 logits, 1,000 probabilities of different classes, and 1,000, that's basically the number of classes for ImageNet 1K dataset. And so the rest of this video will basically be about reading this model inference code. Okay, so let's discuss the overall model structure now. So I have this inference code. Now I need to set the breakpoint into the actual model. The easiest way to do that is to just search for this SWIN tiny model definition in our repo. And here it is. So it is some wrapper that allows you to download weights, verify them, and so on. And then it calls this SWIN transformer, right? And this is the main module that actually does all the work. So you can see that it inherits from an m.module. So it's typically how we write neural networks in Pytorch. And here it has a huge init module and then just forward call. So let's break at the forward call and just see how all tensors are looking like. So I'm pressing the debug cell now. And here we are. We've stopped this forward call. So first let's print what the input looks like. So we get 8 images, each with 3 colors, each of them of the same dimensions, 2:4 by 2:4. Then all of that is passed through the module called features, and that's pretty much everything in SWIN transformer, to be honest. So now the output of that is 7 by 7 by 768. So 768 is the hidden dimension, the embedding dimension in all the attention blocks. And then 7 by 7 is the final downsampled resolution. So by now we've basically gone through all the SWIN shifted window attention blocks, all the patch merging blocks, all of that. So we'll look into that in detail, don't worry. But here is one thing that is interesting. So we've got our 7 by 7 output. We pass that through, we normalize, permute some things, and then call average pooling. And then we flatten it out, by which, like after the pooling, we already get this basically one embedding output for the entire image. And then we also have this prediction head, and the type of that is just the linear layer. So that's an interesting detail as compared to Vision Transformer, for example. So in Vision Transformer, we had our input divided into patches. Each patch, like everything was flattened out and then sent to the self-attentional modules. And then we had one special token concatenated with this sequence. And we also got this special token out. And so thanks to that, we basically had all the predictions of the entire model stored in that token. So we basically, the way to get output from the transformer was to get all the sequence, throw away everything but just one token, and then pass that through your classification head. In case of SWIN transformer, we don't do that. instead we get our patch output as tokens as well. And instead of just getting one of them, because we don't have anything special now, all of them are equal, corresponding to certain positions within the image. So instead we just perform average pooling. So just average them all out, making sure that all of them are contributing to the final classification probabilities. And that's it. That's how we get the final output. So now most of the logic is hidden inside these features. And to understand it, we actually need to read the initialization code. So let me come back here. And to get here, I scroll a little bit up in my Jupyter notebook, and I'll call debug cell on this build model code. Right. So yeah, first of all, let's maybe take another look at what we have. So I have the patch size. So this is like 4 by 4 pixels. Actually, let me show the presentation. So this is how the model looks like, right? So we have our input image. We divide it into patches, and each patch is small. And we start with this quite high number of patches, so that the actual patch resolution is quite high. And then we perform some attention layers. Then we downsample, arriving at smaller patch resolution, and then even smaller patch resolution, and then even smaller, and that's how we arrive at the final. Like here it's plotted as 4 by 4, but we've just seen that the final output is actually 7 by 7 patches. So this is the hierarchical structure when we merge the patches. And it works similarly to convolutional networks, ResNet, for example, where each convolution basically downsamples the image, reducing the spatial size, spatial resolution, but increasing the hidden dimensions. And also inside every stage like this, we have shifted window attention. So instead of full pairwise attention between every patch and every other patch, all this self-attention is limited to interactions within the patch only. And that is the primary thing that limits the computational complexity of the model and allow us to increase the initial resolution. So we compute this window attention. So every patch communicates only to every other patch within the window. And then we shift that as well. So we basically move that with a cyclic shift a bit to the right and down. So now, the patch was here, and now it moved here, and some of it is moved here. We're not actually doing any pairwise interactions after the cyclic shift, so there is no connection between the corners. It's just within this patch now and within this patch individually. But thanks to the fact that we've shifted the window, we basically allow the information to flow a little bit outwards. So we've started with a window like this, and then we've shifted it, and then the same information has spread out half the window size. And then we perform that stage by stage. So we merge some patches. The window size is constant. So now every patch is bigger. So now the effective area covered by our attention also increases. We shift it once. We merge some patches again. By now, the window size is so large that it actually covers all the image, and that's it. So we do it a few times. And so the depth number here is basically number of these window attention layers within its stage. So we perform 2 window attentions in the first stage with the highest resolution, then downsample, then 2 more, then downsample, then 6 more, and so on. Embedding dimension is the starting dimension, but it's basically multiplied by 2 after every downsampling. This is the window size. It's 7 by 7, it's constant across stages. This is the number of heads. So heads come from multi-head attention. So we're not just computing these pairwise interactions once. We actually compute them n times, where n is the number of heads. And again, the number of heads keeps increasing the deeper we go. And we also have this stochastic depth that we'll discuss later. So now coming back to our initialization code, let's actually read this. So this is just the initialization. So we don't have any input right now. The main block is the SWIN transformer block. That's we will look at a bit later. So the yeah, like the final thing that we'll apply is this layers. So we initially just construct it as a list, and then we create a pytorch.nn.sequential module out of that. So that's basically a way to apply the same thing layer by layer. So we start with this initial patching operation. So let's print out what is the patch size. It's 4 by 4. And at this point, we basically get an image, which in ImageNet case is 2 to 4 by 2 to 4. And then we split it into patches. And this patching operation, let me show it once again. So here's the patching. So we had our image, and then we divide that into non-intersecting patches. So that one is actually a special case of just a convolution. So yeah, that's how it's written in code, convolution. But thanks to the fact that kernel size and stride are exactly equal, this is like dividing the image into non-intersecting parts. So this is the patching operation is basically implemented through the convolutions. So now after this, we have split the image into collection of patches. So 4 by 4 patches, 2 to 4 by 2 to 4 image that yields 56 by 56 patch resolution. And then we iterate over stages. So each stage corresponds to a certain resolution we have. So we start with 56 by 56, perform some layers, then downsample it to 27 by 27, then cut it in half again, and that's it. And within every stage, so we have this stochastic depth. We'll look about it later. And we also have this SWIN transformer block. So SWIN transformer block is the one that actually performs attention. So that one will have the shifted attention mechanism. It will have the residuals. It will have some dense layers on top. That's how usually the transformers work. So the only difference of that one, apart from stochastic depth, is the fact that instead of full attention, we actually use this shifted window attention. What else? This shift size, that basically says by how much we shifted. And you can see here that it's either 0 for layer number 0, layer number 2, layer number 4, and so on. And it's window size divided by 2 for every odd layer. So layer number 1, 3, 5, etc. So we start with no shift, then we shift half the window right and down, then we return back, then we shift, return back, and so on. So we only move in this half window size period. Right, so here we iterate over these depth, and we can plot again. That's 2 on the first stage, 2 on the second stage, which corresponds to just normal attention and shifted attention. Then on the next stage, we have 6, and then 2 again. And then after we have constructed these shifted window blocks, the final one will have this downsample layer. And the downsample layer is this patch merging block. So this is the one that reduces the patch resolution after the end of every block. Sorry, after the end of every stage. Now let's discuss stochastic depth. So we can see the stochastic depth probability defined somewhere here. For SWIN tiny, it's equal to 0.2. And then to initialize the actual probability of stochastic depth of every layer, we basically have this formula, which ends up being linear, increasing from 0 to 0.2 over the depth of the network. So the first layer will have survival rate of 1.0, then slightly less than 1.0, and so on, and it will decline to something like 0.8. So let's see that in action. So yeah, first layer stochastic depth prob is 0, then 0.03, and then if we keep going, it will keep on increasing to 0.14, and then at the very end, it is equal to 0.2. Right, So what it actually is. So we can see that this stochastic depth probability is being passed to the block. So the block in this case is this SWIN transformer block, and we can make sure in that. Yep, that's SWIN transformer block. So let's just go to definition. Again, it's a Pytorch module. It has initialization and it has forward method. And the forward method basically, so this is this main transformer block. So it's one layer in our multi-layer network, and it's going to perform, it's going to take this collection of patches, so the image divided into patches. Then, as you can see here, it applies normalization, then self-attention, and then on top of that, stochastic depth. Then this plus here is basically for residual connection. So residual skips the attention and just connects the output directly to the input. And then the same for multi-layer perceptron. So this is like the bunch of dense layers on top of the attention. So let's go to the stochastic depth. Stochastic depth again. And here is the code for it. So it refers to this paper. The paper is from 2016, so it's quite an old paper, about from the same time, slightly later than the actual residual connections. Let's just break at the very end of it and actually see it in action. So I'm coming back to the cell with model inference. I'm pressing debug cell, and here I am. So now the survival rate is 0.98. And so what do we do here? So input to this is just our input image separated into patches. So at the moment we have batch size of 8, 56 by 56 patches, and then 96 is the hidden dimension. And then what do we do here? So we have this survival rate, which is close to 1 at the moment, and then we generate this Bernoulli noise. And for those of you who don't know, Bernoulli noise basically generates ones and zeros, and it typically will be ones, but in 2% cases, it will be zeros. So let's see if we are lucky. Nope, just ones at the moment. So let me move forward again and see the stochastic depth for the next layer. So again, let me print the shape of the input. The shape is still the same, so that's probably the second layer on the same stage. Survival rate is the same, and the noise is all ones again. Okay, let's do it a few more times, just to be safe that we get something interesting. So input shape. Okay, so input shape is down to 14. So we've cut it by half once, 56 to 27, then did a couple of more layers, then cut it by half again. Now coming down to 14 by 14, and now the hidden dimension is 4 times larger. So survival rate is significantly smaller. Now it's 0.92, and the noise is, yeah, and we finally see our first zero here. So what this basically does is, remember, this thing wraps stuff inside the SWIN transformer block twice. So once when we apply the self-attention layer, and another one when we apply the multi-layer perceptron. And we have 8 images in a batch. And what we do here is basically, with roughly 8% probability, we just zero out the layer for the entire image. So 7 out of 8 images got through without any modification, although not without, but they were multiplied by this 1.07, and this is for basically maintaining the same distribution. So our survival rate is slightly less than 1. So we sometimes multiply by 0, and in other cases we multiply by 1.08 to bring the mean to the same level. And so sometimes it will just zero out entire layer prediction for this image. So it's not critical, because we still have this residual connection. So what this does is basically it allows the computation to completely skip one layer in some cases. So I'll link this paper in the description. It's quite an interesting read. And basically the idea behind stochastic depth is that it is a sort of dropout mechanism, but applied to the depth of the network instead of width. So if you remember the dropout, you have, 1024 predictions of the layer, and you would zero out 10% of that. So this is like saying that I have this width, and I randomly reduce that, and only during training. So during training, the effective width will be 90% of the original one, and then during inference, it will be back to 100%. We have the same here with stochastic depth, but now instead of width, we modify depth. So sometimes by multiplying this entire layer by 0, we just throw away an entire layer. And thanks to the skip connection, we just connect input directly to the output. So it's the same as just skipping this entire layer completely, which is to say that we have our depth, and during training, that depth will be decreased by something like 20%. Well, it's actually less than 20 because the survival probability or this noise rate rises linearly from 0 to 20. So it will be 0.1 on average, which means that in the effective depth of the network is only 90% of the original, and we randomly zero out entire layers during training. But then during inference, we are not doing that. And this is how we basically have smaller, less deep network during training, which speeds up the training, makes it a bit more effective, but we still have this effective long, huge depth during inference. So if you can see here, so we can come back to this stochastic depth definition, and it actually checks if we are in the training mode, right? And then if we are not, we just return. So this whole zeroing out of layers only happens during training. So it's not happening during inference. So you have effectively shallower network during training, helps speed it up, helps make it more effective because of the of challenges with training deep networks. But then during inference, you would have your original depth back. So it's a small detail. It's the first time I've seen it, even though the paper came out in 2016. But I guess it's interesting to have that. It's interesting that it's a small addition that I believe helped. So you never know. Okay, now let's discuss shifted windows attention. This is the main component of the entire network. And this is the reminder how it works. So we have our image divided into patches. In normal full self-attention, like in Vision Transformer, we would have just all the pairwise connections between every patch and every other patch. So in window attention, we basically have we further divide the image into windows, and we limit this pairwise interactions to within one window only. So we let this patch connect to this patch to this patch, basically all the patches within this window, and then the same for this window, but not between the windows. And we do this one layer of just self-attention like this, the same way we do it in normal transformers, but now with this limited visibility. And then we shift it by basically doing this cyclic shift. And now this corner only attends to itself, this corner only attends to itself, everything else is the same. So there's, despite the cyclic shift, there is no pairwise connection between these corners. So now let's look at this in code. So I'm coming back to my SWIN transformer module. And here, like basically the main layer is defined as SWIN transformer block. So let's go to that one, go to forward method call. We've seen this before. This is the one that calls stochastic depth. And the main component here, so it takes in the image, normalizes it, and calls this attention. So yeah, let's just break there and see what happens, and then also add a breakpoint on the actual attention block itself. So let's run this. Okay, so this is the forward call. So the shape of that is 56 by 56. In the later layers, the shape will gradually go down and the embedding dimension will go up. Then after this first attention call, the shape is exactly the same, and the same goes for this MLP block. So once again, typically attention layers don't change the shape. So the output sequence length is the same as the input sequence length. An interesting detail here is that we actually operate on 2D data. So we're not flattening that out, although we do that internally when we actually compute the attention, but we make sure to return the output back into this 2D shape as well. So now let's dig into this shifted window attention now and try to read it. So yeah, most of this is inside this functional call. So let's go to that one and just break here. Boop, boop. Okay, I'm here. So let me print out the input shape. So still the same shape, although I did probably iterate a couple of times, so I might have the shift size non-zero right now. Yeah, which is even more interesting. Right, so what do we do here? So we know how it works in principle. So we basically compute the same attention, but now within windows only. And so let's look at how that actually happens. So first we do some padding in case a window size is actually greater than, like in case the window will basically cover only part of the edge of the picture, which is not the case for the first layer. Then we obviously check if window size actually covers the entire image. And if it does, then we don't need to worry about the shifted attention. We just basically perform normal attention. And then this is the cyclic shift. So it calls this torch.roll operation. And with operations like this, it's typically easier to read because you sort of understand how it works by shifting everything with the specified shift size. It's much harder to write that down, especially in CUDA code, and it's much harder to basically use that code when you need to write that from scratch. Thankfully, we're not doing that here. We're just using what is already written. So here, yeah, I basically just cyclically shifted the entire image. So now my attention windows will get shifted as well. So yeah, I compute the number of windows. And then the next crucial thing here is this view. So let me print the shape of X before I did this, and then after. Right. So let's discuss what's happening here. So first of all, I had my 8 batch size and then 56 by 56 image. And my window size is 7 by 7. And 56 divided by 7 is 8, which means that I now have 8 by 8 windows covering the entire image. And I basically split the stanza, reshaping it. So it's an easy operation, meaning that it actually doesn't copy any data around. It just says that, this stanza now have a different shape. And I basically split the tender into windows like these, like square windows. We are basically lucky that the default implementation of this view method performs this exact square indexing, right? So it's not doing anything weird. It's not selecting like row by row or anything. It does exactly this window-based selection. So we are just lucky here. I mean, or Pytorch creators really thought about that really hard to how to make it the most convenient. So this is like the core operation here. And then once I did that, so I do some permutations and reshape, and we'll see the result of that now. So after all of this, I now have 512 by 49 by 96. So now, and now it's flattened basically. So what is happening here? So typically, transformer receives a sequence as an input. So it has a batch dimension, it has a sequence dimension, and the embedding dimension. right? So we've started with just an image, which instead of a linear sequence had 2D, so 2 dimensions, the height and width. We further split it into windows, turning 2 dimensions into 4 dimensions instead of 1 as we needed. Then we reshaped it in such a way that this windows, everything that needs to interact with each other got into the same window. And then we reshape it again so we had 7 by 7 window, and 7 multiplied by 7 turns out to be 49. And so we have this 49, and we just flatten it out into a single sequence, and everything else is moved into a batch dimension. So this is the same as saying that I had my picture, I've further divided it into several windows. I had a batch of such images, and then I just flattened out all the windows, all the batches. And so I have this first image, first window, first image, second window, second image, first window, and so on. All of that is now in the batch dimension. But now the second dimension is exactly what I need. So the second dimension actually refers to the position of the patch inside the window. And this is my new sequence of elements. So this is where I actually get this pairwise interaction. So we'll have attention calculated over this 49 patches. And now we would just see the code that is similar to normal attention code. So I have my X vector tensor. I project it down to query key and value. For simplicity, it's using just the same set of weights. Sorry, not the same, but 3 sets of weights concatenated into a single vector. Then I reshape it to get out my query key and value. All of these right now should have the same shape. Query key value. Right, so let's look into that. So 49, as we've told, is the new sequence length. 512 is this new effective batch of all the windows flattened with all the images. And now I had my hidden dimension of 96, but I also have multi-headed attention. And it's typical for multi-headed attention to divide the initial embedding dimension into n parts, where n is the number of heads. And so here we divided it into 3 heads, each getting the 32 numbers from the embedding. And here we do some scale change, basically, and then calculate the attention. So this is the core of attention. This is the attention matrix. And we computed that as just matrix multiplication, right? So we had query of this certain shape, key of the certain shape. And it's easy to think about matrix multiplication as something that basically removes 2 dimensions, right? So like if you think about vector multiplication, right? So you had one vector, which is a row, another vector, which is a column. So at this point, every one of them has 1 dimension. And then you collapse that down, removing this dimension and this dimension into just one number. Similarly, if you have this long tensor of 512 by 3 by 49 by 32, and another one like this, so this, depending on how you transpose the input, you choose which dimension to remove. And in this case, we multiply an embedding by an embedding, effectively removing dimension of 32 from one tensor and from the other tensor. And so the result will be just the batch times heads times this 49 by 49. So basically, batch dimension stays the same. The sequence dimension got concatenated. So we have 49 by 49 as the embedding dimension got collapsed away. So now our attention shape is 512, same batch dimension, 3, same number of heads, but now we have 49 by 49, which now shows the attention weight between every patch out of 49 within the window to every other patch. And yeah, right. So the next interesting thing that we do here is this relative position bias. So I think we've skipped the code for actual initialization of that. So maybe let's fix that. Let's find where it is. Okay. So it's actually defined in this shifted window attention module. And we can see here that when we do the forward path, okay, so we initialize this shifted window attention, and we pass in this basically parameter tensor, right? So it consists of trainable parameters. They are initialized in such a peculiar way because initially we need to calculate this relative positional bias between every potential pair of patches within the window. But actually not all of these pairs will have a unique embedding, because, for example, this guy interacting with this guy should have the same relative position bias as this guy interacting with this guy. So it's the same as saying that we don't refer to any unique pair. We just have one unique embedding for every coordinate difference, basically. So this one is saying that it's not this guy to this guy, it is one to the right and one down. And so this one to the right and one down, will have exactly the same embedding. And so in code, it looks like this relative position table, which is smaller, but then we expand that to all pairs, basically allowing these non-unique pairs to reuse the same weights. Right, and where was I? Okay, and the way we use that in our attention calculation is that we've calculated the actual attention matrix, and then we just add the weight to that. So this is the relative attention, basically. Then another interesting thing is this attention mask when there's a shift. So right now, as I've told you, we've divided the picture. We've shifted it like this. We've divided it into equal size windows, which means that in our calculation right now, this corner here and this corner here actually were in the same attention calculation, as if they actually can interact with each other, right? But we don't want them to actually interact. We want to keep our interactions local. So we do that simply for performance reasons. So we basically put them into the same window to save up on cost, on compute. But now we don't want for them to actually interact. And because of that, we just zero out pairwise interactions corresponding to this cyclic shift from one corner to the other. And this is what happens in this code. So now we see if the shift is there, we need to apply certain attention mask. Right. So let's move here. So we do softmax, we do dropout, and that's all for attention, right? So for now we had queries, keys, and values, all initialized from the same input patches sequence. Now we have our attention matrix, which is 49 by 49 in our case, and we multiply that by our value. So again, value shape is 49 by 32. Now the 49 dimension will be the one to go away. But since I had it twice in the attention mask, I basically get out the same shape. So let's see how it looks like. So X shape is, again, 49 by 96. So I'm back to my original shape. I've computed my attention pretty much by this time. Apply another linear layer, drop out, view and permute to return it to the original shape. Yep, and I'm back to my 56 by 56. So I've had this 49 dimension basically responding to the size of the window, and then all the other dimensions were shifted to the batch dimension. Now I perform the reverse operation, coming back, basically reassembling all of my images. So batch dimension is back to 8, and I've just expanded all my windows back to its original places. And yeah, if there was a shift, I shifted back again to return my original image. And that's it. So this is shifted window attention. Final interesting detail about shifted window attention is that it's really, really fast. So everything we've done here, the linear projections, the torch.roll, so that's a quite effective operation, basically moves the data around, which can be done in parallel. The view operation is just metadata level. It's not really copying or moving data anywhere. And then the actual attention is still matrix multiplication, and then another matrix multiplication. So the reason this works really effectively is that we basically wanted an attention-based operation that will be similar to convolutions in some sense, in that it's local, but it's also somewhat expanding and allows information to flow outwards. And there were previous attempts to do that, like sliding window attention. And the shifted window attention, its main benefit is that it basically uses matrix multiplications. The same one used in the normal attention, the single most popular operations in the overall linear algebra. So you can really be sure that it's really effective. And because of that, thanks to the fact that we managed to perform our operation through that simple matrix multiplication without custom CUDA code, without some advanced techniques or data copying or anything like that, thanks to that, it's really working really effectively. Now let's discuss the final thing called patch merging block. So coming back to the code, let me come back to SWIN transformer. The initialization block, so it initializes the stages with the SWIN transformer block, and then after the end of every stage, it has this downsample layer, which is itself patch merging. So let me just, and this calls the patch merging pad function. So yeah, let me just put a breakpoint here, and let's launch this once again. I'm removing this old breakpoint in the attention, in the stochastic depth, and here I am at the patch merging pad. So the input of that is my first patch, right? So it has, so we started with the image, we've divided it into patches. We've passed that through two self-attention layers at the moment, and the shape is 56 by 56. So now what I'm doing is I want to collapse 4 patches into one. And this is how I do it. So I first select these 4 patches. So each of these is a tensor. So it's like this one is selecting even block, this one is selecting odd even block, this one is selecting even odd, and this one is selecting odd odd. So basically each of these selects like a 1 out of 4 squares in every 4 square patch. And then I concatenate all of them together. So I selected 3 of these, I concatenated them. And this basically means that I've collapsed my image dimension by half. So it's now 22 by 22. Now the embedding dimension, because I've just concatenated 4 squares together, basically, 4 patches together, embedding dimension increased by x2, right? And so after that, let me come back to where I was in the patch merging and add another breakpoint here. So after this merging, I do normalization, and I call this self.reduction, which is itself just a linear layer, which basically projects the 4x hidden dimension down to 1x. So after this, I've got 28 by 28 by 192. So this is the patch merging block. This is analogous to convolution with stride. So it takes in an image, it projects the resolution down by half, and it increases the channel dimension by x2. And this is pretty much it regarding the SWIN transformer architecture. So I hope it was useful. I hope it clarified some problems you might have had by just listening to the video or reading the paper. In addition, I want to take some time to explain what else do I have in my channel. So a lot of recent videos were focusing on object detection. So this video was about reading SWIN transformer source code. Before that, I have a video about the actual SWIN transformer. I also have a lot of videos about other object detectors and image classification models. So I have a video about VAT, about the whole Dettor family of models, about YOLO. So I have a video about Dettor, deformable Dettor, DAP Dettor, denoising Dettor, and one video for every model explaining the actual algorithm, and another video actually reading the source code and helping you set it all up and reproduce. And the very next one will be about the famous model called Dino. So it's a state-of-the-art object detector, although not anymore. There's a new one called Codator, and it basically unifies a lot of concepts of SWIN backbone, the one we've talked about just now, of deformable debtor, depth debtor, denoising debtor, and all of that. So all of that basically leads up to this really famous model, which I think pretty much proved that debtor-like family of the models can be better than anything else. So before that, we've seen a lot of models, but they had a nice concept, a nice simple concept behind them, but they never quite reached the quality of other models like, I don't know, regional proposal networks and so on. And Dino was the first one to actually overcome all of that, which basically means that, you can just focus on the transformer-based models and forget everything else. You don't need to know how regional proposal networks work, because that's outdated by now. And that's really nice because it just saves you a lot of time. So anyway, that's what my next video will be about. Then we'll talk about Codator. And that's not it. I have a plan for a lot more videos, so we have a lot to cover. See you soon.